Hello, and welcome to this presentation, Understanding Filter Measurements. In this presentation, we'll explain the basics of radio frequency filters, as well as explain how filters can be measured using different types of test and measurement instruments. Let's start with a general description of a filter. Radio frequency filters are two-port devices that attenuate the power of RF signals passing through them as a function of frequency. Even though this attenuation is never perfect, filters are commonly described as passing certain frequencies and blocking or stopping other frequencies. Filters are critical components in almost all radio frequency devices and applications. They may be implemented at the board level using discrete components, or they may be packaged/connectorized devices. And as we'll discuss in just a few moments, a wide variety of instruments and techniques can be used when designing, adjusting, or measuring filters. Filters are normally divided into four general categories: low pass, high pass, band pass, and notch or band stop filters. A low pass filter blocks signals above a certain frequency. That is, it passes low frequency signals. The opposite of this is a high pass filter, which only passes higher frequency signals and blocks signals below a given frequency. A bandpass filter can be thought of as a combination of a high and a low-pass filter. Only signals with frequencies within a certain passband are allowed to pass through it. And finally, a notch or band stop filter is the opposite of a bandpass filter. It allows all signals through except for those falling within a certain frequency range. Note that typically this notch is much narrower than the passband of a bandpass filter. Regardless of type, most filters have fixed parameters, that is, type, frequency range, attenuation, bandwidth, etc. In some cases, the properties of these fixed filters can be adjusted by using screws or similar methods. However, these adjustments normally require special tools and/or procedures and are typically done during manufacture. That said, some filters are designed to be adjusted on a regular basis by the end user, and these are called tunable filters. An example of this would be a bandpass filter, whose center frequency can be manually changed by turning a knob or dial. Next, let's discuss how filters are measured. Measuring filters involves injecting a signal into the input of the filter and simultaneously measuring the output of the filter. And this can be done with two different types of signals. One method is to use a wideband noise source as a signal, since this signal will contain power over a wide range of frequencies. The other method is to input a narrowband or CW signal, which is then sequentially stepped through a range of frequencies. This is by far the more common way of making filter measurements. As we'll see later in this presentation, there are many ways to quantify filters, but the most important of these is attenuation as a function of frequency. Other common measurements include phase shift, quality factor, etc., and we'll cover all of these in more detail shortly. Measurement results are often plotted together with important numeric values, and in many cases these plots and values are automatically produced by the measuring instrument. Four different types of test and measurement instruments are commonly used to measure filters. These are vector network analyzers, spectrum analyzers, power sensors, and oscilloscopes. In the next section of this presentation, we'll briefly describe how filters are measured using each of these different instruments. A vector network analyzer is an instrument with one or more ports, each of which can act as a source and/or a receiver. In the case of filter measurements, one port sources the input signal to the filter, and another port is used to measure the filter output. This is often referred to as an S21 measurement. VNAs are generally considered to be the most flexible and feature-rich method of measuring filters, and they provide many advantages. As their name implies, VNAs can make vector measurements. That is, they can measure both the magnitude and the phase of a signal. They also can have a very high dynamic range, which is particularly important when measuring high-performance filters. VNAs can also be calibrated to provide high accuracy and to remove the effect of cables, etc., from the measurement results. Many VNAs also have automated filter measurement functions, for example, determining the center frequency, bandwidth, etc., of a bandpass filter. And since VNA ports can source and measure signals simultaneously, they can measure the signal reflected from the filter input, as well as measure in both directions without requiring the test setup to be recabled. Filters can also be measured using a spectrum analyzer and a so-called tracking generator. Similar to how a VNA works, this generator produces a signal whose output frequency is coupled to or tracks the measurement frequency. Sometimes this tracking generator is internal or integrated into the spec-an, but it may also be an external signal generator whose output frequency is controlled by the spectrum analyzer. In either case, a sweep is run with a filter connected between the tracking generator output and the analyzer input, with the results being displayed on the analyzer itself. Depending on the instrument and generator, measurement results may be scalar, that is, magnitude only, or may have phase information as well. And like VNAs, this approach can also allow normalization or calibration to remove the influence of the test setup. Another way to measure filters with spectrum analyzers is using a wideband noise source. This source is usually controlled and powered from the spectrum analyzer and produces uniform power over a fairly wide frequency range. This wideband noise is used as the input to the filter, and the filter output can then be measured to determine the filter response. Note that only the scalar response of the filter can be measured in this way. Another thing to keep in mind is that many noise sources have relatively low output power, so a preamplifier may be needed between the noise source and the filter under test. In addition, the noise source should have a more or less constant power level over the frequency range of interest. And finally, averaging the measurement traces on the spectrum analyzer can be helpful in getting clear and precise measurement results. Filters can also be measured using RF power sensors, even though most power sensors are not frequency-selective devices. In this case, a signal generator provides a narrowband signal or tone that is stepped over a user-defined frequency range, and this stepped signal is used as the filter input source. Ideally, the sensor is connected to and controlled by the generator, and this same connection is used to measure power at the filter output at each step. Software within the generator can be used to plot the filter response, although this could also be done manually or by means of a user-created program. However, like the wideband noise source method that we looked at just a few moments ago, this measurement method only provides magnitude information. Oscilloscopes are primarily time domain instruments, but they can also be used to measure the frequency response of filters. To do this, either an internal or external function generator is used to provide a stimulus signal that sweeps over a user-defined frequency range. The output of this generator is connected to the filter input. One oscilloscope channel is used to measure this input signal, and another channel measures the filter output. The scope then plots the difference in magnitude and phase between the input and output signals as a function of frequency. These are typically displayed in the form of a so-called Bode plot. Because we're looking at filter response as a function of frequency, this type of measurement is often called frequency response analysis, or FRA. Be aware, however, that many oscilloscopes, and in particular most function generators, have limited bandwidth compared to vector network analyzers or spectrum analyzers, and therefore frequency response analysis on oscilloscopes is typically limited to frequencies of about 100 MHz or less. It's also worth mentioning that there are other ways of measuring filters using an oscilloscope, but these tend to be more cumbersome and less precise, and therefore we won't be covering them in this presentation. Now that we've covered measuring instruments, let's go over some of the most important filter measurements themselves. These are passband, stopband or rejection, insertion loss, ripple, group delay, quality factor, and input impedance. It's important to keep in mind that while all of these quantities can be measured using a vector network analyzer, some are not available using other instruments or methodologies. By convention, a signal is usually considered passed by a filter if it's attenuated by 3 dB or less. Therefore, the passband of a filter is commonly defined as the frequency range over which it attenuates signals by less than 3 dB. For example, in this bandpass filter, signals are attenuated by less than 3 dB between these points, which are sometimes referred to as cutoff frequencies. The most fundamental characteristics of a bandpass filter are its center frequency and its passband, or the distance between the 3 dB points. Note that the stop band of a notch filter is defined in a similar way to a bandpass filter. Low-pass and high-pass filters, on the other hand, have only a single cutoff frequency, and this is used to define the filter response. By convention, filters are said to pass signals with less than 3 dB of attenuation and block signals which are attenuated by more than 3 dB. Attenuation does, however, continue to increase beyond these 3 dB points, and the frequency range over which attenuation increases is often referred to as the transition band. The rate at which attenuation increases, or the slope of the attenuation curve, is a function of filter design, and generally speaking, steeper slopes within the transition band are more difficult and/or more costly to obtain. The region where attenuation becomes more or less constant is called the stop band. The stop band is an important filter parameter and is defined as the frequency range, or offset from the center frequency, where attenuation or rejection is greater than n dB. Common values of n are low tens of dB to well over 100 dB, and here again, this is a function of filter design, with higher values of n typically corresponding to higher cost and/or complexity. From a test and measurement point of view, it's important to remember that instruments typically require a high dynamic range and/or low intrinsic noise to measure filters with high stop-band attenuation or rejection. In addition to attenuating signals outside of their passband, filters also unavoidably attenuate signals within their passband, and this is referred to as insertion loss. For most well-designed filters, insertion loss is on the order of a few dB or less. Insertion loss is primarily caused by impedance mismatches, as well as by dissipative losses within the filter. In the ideal case, insertion loss would be relatively constant, or flat, over the filter passband, as shown in this example. Variation in attenuation within the passband is referred to as ripple, and passband ripple is generally undesirable. Note that there can also be ripple in the stop band, but we're usually most concerned with passband ripple. Both insertion loss and ripple are usually relatively small quantities, so proper calibration and high instrument accuracy are important when measuring these quantities. In addition to attenuating signals, filters also delay signals passing through them, but in most cases the absolute delay or phase shift caused by a filter is unimportant. That said, this delay or phase shift should be the same for all frequencies. If there is variation in delay as a function of frequency, this can create distortion in complex or modulated signals passing through the filter, since these types of signals often have power at more than one frequency. Group delay is the term used to describe measuring or quantifying this delay or phase shift as a function of frequency, and is another important filter measurement. For example, if we measure the group delay of a bandpass filter, we often will see peaks in group delay near the passband edges, and in this case it might be advisable to use a filter with a passband slightly wider than the signal we wish to pass. Group delay can be measured using either a vector network analyzer or a spectrum analyzer plus signal generator, with results most often shown as plots of phase deviation as a function of frequency. Another common filter measurement is quality factor, or Q, which is generically used to describe the selectivity of a tuned element. Another way of saying this is that Q describes the slope or steepness of the transition band relative to the passband. This most often is used to describe bandpass filters. A filter with a high Q will have steeper slopes in the transition region compared to a filter with lower Q. Q is quantified by dividing the center frequency by the bandwidth of the filter. Recall from our previous discussion that the bandwidth of a filter is typically defined using the 3 dB points. Regardless of the type of filter, most filters are reflective. That is, they attenuate signals by reflecting them back towards the source. For example, this low-pass filter passes signals below 450 MHz by reflecting higher frequency signals. In more specific terms, reflective filters present a good impedance match in the passband, but a poor impedance match in the stopband. The impedance match at the filter input as a function of frequency can be quantified by using a VNA to make a so-called S11 measurement and displaying the results as return loss or standing wave ratio. Although the vast majority of filters are reflective, special absorptive or reflectionless filters can be used for devices that cannot tolerate high levels of reflected power, such as broadcast or other high-power transmitters. And the input impedance of these types of filters can be measured in the same way. Let's end with a brief summary. Filters are RF components that pass or attenuate signals as a function of their frequency. They may be connectorized, as shown here, or be in the form of packaged or discrete components. Filters are typically categorized as high-pass, low-pass, bandpass, or band-stop/notch filters, depending on the frequency ranges they attenuate. Filters can be measured or quantified using a variety of different instruments, including vector network analyzers, spectrum analyzers, RF power sensors, and oscilloscopes. Although there are many different measurements that can be made on filters, in this presentation we covered the most important ones, namely passband and stopband or rejection, insertion loss and ripple, group delay, quality factor, and input impedance. This concludes our presentation, Understanding Filter Measurements. If you'd like to learn more about RF filter measurements or about test and measurement instruments for measuring filters, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.